Good morning, everybody. Good afternoon, everybody. We're here for quite a simple reason, because within the debate about climate change, there are many reasons to worry. I will not tell you what we talked about in the previous during the previous conference. It's sure that our planet is victim of global warming. We use fossil fuels to produce energy, and we discharge into our atmosphere CO2 and other polluting gases. Therefore, we basically cause global warming, and the CO2 stays in the atmosphere for thousands of years. 1/5 remains for thousands of years. So it will go on warming our planet. We're already seeing the consequences, and the science tells us that the more the temperature increases, the more the climate will get warmer. So also here in our territory, we're starting to live some very hot summers, and we need to stop and think it over. We'd like to see some positive trends, something which can give us hope for our battle against climate change. We just need to know that we can have positive and important results. We invited Mark Jacobson because he's maybe one of the people in the world who is best demonstrating, who is best showing how many things we can do to fight against climate change, especially as far as we need to change our our energy system, which is based on fossil fuels, and we need to transition to a 100% renewable energy system. So after this short introduction, we will hear Mark Jacobson talking for about 45-50 minutes, and then we will have a Q&A session. I invite you to see his speech under this point of view. I like following him on Twitter, and I suggest that you follow him on Twitter. I like the papers, the articles that he publishes, because he is always publishing trends about positive trends against climate change. We know that the climate change problem is not a technological issue. It is something which concerns the culture, philosophy, politics. But today we'd like to see what's happening as far as today's perspective is concerned. We're focusing on the technological perspective. Our territory is basically promoting energy efficiency, and Mark will also talk about various reasons why it's worth it to do something more in the future. Since 2017, Mark is professor at Stanford University in the Civil and Environmental program. He published a lot of scientific papers, more than 200. Just to give you an idea, you know that last week there was a quite sad TV show where they hosted a so-called expert who was telling that renewables are not feasible. And well, that professor published only 2 papers in 25 years, whereas Mark published 200 papers, just to talk about the level of expertise. In the past, he dealt with the effects of particulate matter in the atmosphere. He developed some models, and today we're here to listen to him talking about decarbonization, that is to say, producing energy without fossil fuels. In 2011, he published a very important work on energy policy, which is a magazine, and this paper talked about producing energy for everybody thanks to wind, water, and solar energy. So only this solution. And he outlined how we can actually solve the problems linked to their intermittency and the fact that they are not homogeneously distributed. He also prepared some scenarios, some decarbonized scenarios for all the states in the United States, but also for the countries. I suggest you visit the Solutions Project website, which shows a different mix of solutions for every country in the world. I'm really happy to be here and to have the chance of listening to Mark Jacobson's speech. The floor to you, Mark.
Thank you for that kind introduction, and good evening, everybody. I'm going to talk about the energy plans we've been developing for the last 10 years now on how to transition countries, cities, towns, individual households into 100% clean renewable energy ones. In fact, how to transition the entire world. And the motivation for this is threefold. Not only global warming, which is a rising and increasing problem that risks the entire planet, but also air pollution. 7 million people die every year from air pollution from fossil fuels and biofuels. And this is a problem that is avoidable through transitioning to clean renewable energy. The third problem that we're trying to solve is energy security, because fossil fuels are limited resources and they will run out over time, and that will lead to social, political, and economic instability. So we're trying to solve all three problems at the same time. And really the only way to do this is to transition all our energy to just clean and renewable energy, and then to eliminate additional sources of non-energy combustion emissions. So the basic idea of how to solve the problem is to electrify everything. So, and then provide that electricity with clean renewable energy. So for example, for transportation, we would use electric vehicles and then some hydrogen fuel cell vehicles for long-distance heavy transport, like long-distance aircraft, long-distance ships, long-distance trains even. But even the hydrogen would be produced from electricity in that case. For buildings, we would electrify those as well. Instead of using gas heaters or oil heaters or wood pellets, we would use electric heat pumps primarily, which use 1/4 the energy as combustion. And heat pumps can be used not only for air heating, but also water heating and air conditioning. And for stoves, instead of gas stoves, we'd use electric induction cooktops, which boil water in half the time as gas, for example. And in industry, we would electrify those with electric furnaces, arc furnaces, resistance furnaces, induction furnaces. These are all existing technologies, and replace coal, oil, and gas burning for high temperatures. And we provide this electricity, as I mentioned, with 100% wind, water, and solar. So that's onshore wind, offshore wind, utility-scale solar photovoltaics on rooftops and in power plants, and concentrated solar power. And we'd also use some geothermal power, which Italy has a bit of, and also existing hydroelectric power and small amounts of tidal and wave power. And we would also need storage, but I'll get into that. Let me first just show you some examples. Of course, wind power and solar will be the dominant forms of electricity in this new paradigm. Wind and solar are the only two forms of renewable electricity that can literally power the entire world many times over on their own, each one on their own, many times over. You can power the entire world with solar like 350 times over for everything, and wind is about 10 to 11 times over. But we don't need 11 times, we just need one time over. So wind will be onshore, and so we have onshore wind turbines are actually the cheapest form of new electric power on Earth today. They are half the cost of natural gas for new electric power. Solar photovoltaics at utility scale is the second cheapest, and it's almost, in some places, it's cheaper than wind even. But on the right here, we have offshore wind, which is now coming down in price so much that it's even competing. It's competing with coal and gas as well. It's still more expensive than onshore, but there's so much available offshore wind, and the price is coming down so much that once that comes down even more, the game will almost be over because there's just an enormous amount of offshore wind resource. And we can go now far offshore because we have floating wind turbines. On the right is a floating wind turbine, so we don't even need to put poles in the ocean floor. And so this allows us to go far out into the ocean and collect wind. And so wind is just growing by a humongous amount. And just to give you an example, the other thing about offshore wind and onshore wind is you can install it very quickly. Just this week, the largest offshore wind farm in the world was completed, 174 turbines that were 7 megawatts each. It's over 1 gigawatt, will power 1 million homes off the coast of the UK. And it just went in a couple of years. And compare that to a nuclear plant that takes 15 to 20 years between planning and operation. So it's solving this problem with fast deploying solar and wind is the one way that we will be able to accomplish this. Now, solar is also growing very fast and is very inexpensive. And you can put this in many different places, not only on land, but over canals, like on the top left, over water, floating solar over water, like on the top right, on big commercial buildings on the bottom left, and in big solar photovoltaic power plants, in addition to on residential rooftops, which I'll talk about in a little bit later. Then transportation, there's already a big growth in electric, not only small vehicles, passenger vehicles, but also trucks and long-distance buses long-distance trucks and buses as well. On the top left is a Tesla electric semi. It has a range of 800 to 850 kilometers. On the top right is a hydrogen fuel cell semi that by Nikola that can go 1,250 kilometers. So hydrogen, you can go longer range, but for shorter and mid-range, battery electric is more efficient. On the bottom left, we have an electric ferry that's now existing. On the bottom right is a Proterra electric bus. So now tens of thousands of buses are going in worldwide now, electric buses. And also, these large vehicles are starting to take hold. Right now, about 5% of all cars sold in California are electric, and that's growing, but worldwide, the transition to electric vehicles is moving fast. Electric vehicles are very advantageous because they use 1/4 to 1/5 the energy as gasoline or diesel vehicles. Because in gasoline or diesel vehicles, 3/4 to 4/5 of the energy is wasted as heat, whereas an electric vehicle converts almost all the electricity, about 80% of the electricity, to motion, and so you use a lot less energy. So although electricity demand will go up by transitioning to electric vehicles, the increase is much less. It's like 1/4 the energy increase compared to the reduction of oil and gas, or oil primarily for gasoline and diesel. Now, for aircraft, there are already electric aircraft being built, small ones. In particular, on the left side is an electric aircraft prototype. On the bottom right is a hydrogen fuel cell, a 4-seater hydrogen fuel cell plane that has a range of 1,500 kilometers. On the top right is just a drawing of a hydrogen long-distance aircraft. Long-distance heavy transport will likely have to be hydrogen fuel cells with some batteries as well, just because if you have to go a long distance, you don't want to be carrying just batteries. The weight becomes pretty prohibitive after a certain distance. So up to about 1,500 kilometers which are basically short-haul flights. We'd have electric, and beyond that, we'd have hydrogen fuel cell. But just basic things that run on gasoline or diesel today, we would transition to electric, so forklifts, lawn mowers, leaf blowers. We all know how annoying a leaf blower is, not only because it smells, but it's noisy. Well, an electric leaf blower doesn't smell and it's not noisy. So this is a good thing to transition. Now we also need storage in order to go to 100% clean renewable energy, because the wind doesn't always blow, the sun doesn't always shine. And we're going to be transitioning not only electricity, but also heat and cold, and we'll have some hydrogen. So the types of storage will include electricity storage, heat and cold storage, and then hydrogen storage. So for electricity storage, we'd use concentrated solar power with storage. So concentrated solar is most used in very sunny locations. The idea is, well, I'll just show you a picture really quickly. You focus light off of mirrors onto a central tower to heat a fluid, such as a molten nitrate salt. That fluid is then stored. It can be stored overnight, and then when you need electricity, you pass the hot fluid by water to evaporate the water. The steam from the evaporated water runs a turbine to generate electricity. So you can generate electricity with concentrated solar 24 hours a day. And the cost has come down on that as well, but it's a form of storage that helps keep the grid stable. Pumped hydroelectric storage is another form of storage where you have two reservoirs, a lower one and an upper one. When you have excess electricity, you pump water up a hill. When you need the electricity, you let the water drain down the hill to run through a turbine to generate electricity. Existing hydroelectric dams are basically big batteries, because you can turn them on and off pretty instantaneously to generate electricity. In fact, you can turn on and off a hydroelectric dam to produce electricity faster than you can a natural gas peaker plant. And so it's actually batteries and hydroelectric and pumped hydroelectric storage are all faster than a gas peaker plant to generate electricity. And then we'll also need batteries as well. And batteries are coming down in cost rapidly. Flywheels are for very short-term storage of electricity. Compressed air is a niche that I won't go into very much, but also gravitational storage. I'll show you an example of that in a minute. For heating and cooling, this type of storage has been around for a long time and is very inexpensive already. Water tank storage, basically a big water tank where you can store hot water or even cold water. Ice storage, I'll show you an example of that. And then underground thermal energy storage. This is really useful for storing heat seasonally, from summer to winter usually. And I'll show you examples of that. There's three types mainly: borehole, water pit, and aquifer storage. And then building materials can store heat. You can build your home or a commercial building in such a way that it maximizes the retention of heat. And then we'll need hydrogen storage as well. So I showed you this concentrated solar plant. These are just batteries. Batteries are nice for storage for electricity because they don't take up a huge amount of space. You can pretty much put them anywhere. And they respond very quickly. They can give you electricity in milliseconds. So this can save a lot of money for grid operators. And there are several places in the world that have huge battery storage associated with solar and wind now, including in South Australia, in California, in Florida, and many places in the world, in Germany. This is a type of storage that's very new, gravitational storage with solid masses. So on the left, what you have is a device that when you have excess electricity, you basically pull concrete blocks up and basically pile them up. And then when you need electricity, you let the concrete blocks fall gravitationally. That will run a generator to generate electricity. So the generator in reverse is the motor that allows the blocks to be pulled up. And then when you need the electricity, you let the blocks fall down and run through. The energy is created through a generator. Similarly, on the right, these are basically trains that go up and down a hill with either rocks or concrete. So when you have excess electricity, they go up the hill, and then when you need the electricity, you let them go down the hill. And it turns out the efficiency of this, this is very similar to pumped hydroelectric storage, which worldwide, pumped hydroelectric is the major type of storage, aside from hydroelectric dams. But this is very similar, has a similar efficiency, expected to have a similar cost, but it's very new technologies. Now, heating in water tanks and chillers is an old idea, but I should preface that, well, there are two types of main heating systems. One is where you heat individual buildings with their own heating and cooling system. The other kind is district heating and cooling, where you have centralized heaters or boilers and chillers, and then you pipe the heat around or the cold around to buildings. And this started basically in the 1880s. There was the first district heating system was in Manhattan, but it has spread in Europe. It grew a lot. And right now in Europe, especially Northern Europe, there's a lot of district heating. So there's third generation, this is fourth generation district heating. This is actually at my university, Stanford University, where they had there was a gas cogeneration plant that produced 80% of the electricity and the heat for the campus. And it was actually right outside my office. And in 2016, they bulldozed it, got rid of it. And people were wondering, well, where are we going to get the electricity and heat? Well, they just built these two chillers and a boiler. They basically are two cold water tanks and a hot water tank, an elaborate piping system around the university. And then they bought a bunch of solar photovoltaics and put some solar photovoltaics on the building rooftops in the campus. And so they've actually purchased enough solar photovoltaics now, combined with this district heating and cooling system, that Stanford will be the first campus in the world to be 100% renewable for both electricity and heat and cold in 2020. Right now it's about 90%, but they're just waiting to, they purchased a new solar farm and they're waiting for it to be completed. But basically what this does is when, at any given time, the part of the university needs hot water and part of the university needs cold water or air. And so when you generate heat, you have waste cold. When you generate cold, you have waste heat. So instead of letting the waste heat and the waste cold go to the air, it's trapped and then recycled back to the boiler or the chiller. So this is a very efficient system. And to heat or cool these boilers and chillers, they use heat pumps that run on electricity. And so the heat pumps, as I mentioned before, are very efficient. So this is a fourth generation district heating system in that it has both hot water and cold water loops. And it's very efficient overall. Now this is a really interesting case. This is called underground thermal energy storage. This is in Okotoks, Canada, a place called Drake's Landing Solar Community. In about 2004, 2005, 52 homes were built with solar collectors on their roofs on the top left, or on the roofs of their garages. These collectors contain a glycol solution. And during the summer, where the days are long, this is in Canada again, just 1 hour south of Calgary, when the days are long, these solar collectors collect heat. The glycol solution is piped to the building on the right, where the heat is exchanged with water. The water is then piped under this field that had been excavated, and a bunch of boreholes had been drilled, and pipes were put down with U-turns in them. And so hot water will go down, and then the hot water would exchange its heat with the soil, and the soil would retain the heat for up to 6 months because it's been insulated around it. So 6 months later, when snow is on the ground, like on the left, the whole system is run in reverse, and the heat from underground is used to power 100% of the heat for these 52 homes. And while batteries cost about $200 per kilowatt hour of storage, this underground thermal energy storage is less than $1 per kilowatt hour, and it's seasonal. So whenever somebody says, well, we have a huge heating demand in the winter, how are we going to use electricity when the sun's not shining in the winter? Well, this is one of the ways how. You store the heat that you need during summer. The efficiency, by the way, of the system, it's about 68% round-trip efficiency. It's not, those pumped hydro storage is about 85, 87%, so it's much more efficient. Batteries are much more efficient than this, but because it's so cheap, you can afford to be not so efficient with this type of system. But you can do this not only with soil, but also with water pits. In Denmark and in several Scandinavian countries, they have water pits that do the same thing. In the summer, well, here we have water collectors. All those blue rows are solar collectors. In the summer, this heat is collected and transferred to the pit, which is filled with water normally. And the heat is stored in the water, and the water is covered. And that heat stays there until winter time. And the whole system is run in reverse in the winter to provide the heat for this community. And so there are several communities like this. And you can do a similar thing with underground aquifers. There are many places where you have underground layers of water where in the summer you can send heat down, and then in the winter you extract that heat. So this is, many people aren't aware that this is possible, that this is available, but this is part of the solution to a 100% clean renewable energy future for us all. Here's another type of storage that many people are not aware of. It's called ice storage. Actually, in 1998, my university, Stanford, put a big ice cube like this under a building. And during the night, when electricity price was low, the electricity was used to create ice. And then during the day, when the electricity price was high, instead of using air conditioning to cool the buildings, they'd run water through the pipes and then send the cold water to buildings and cool the buildings. So this is exactly like a battery, because a battery, basically, you need a battery to run the afternoon electricity, the air conditioners, right? But we don't need the afternoon air conditioners because we have cold water here that's stored starting at nighttime. So you basically put in the electricity at night and create ice, and then during the day, instead of using electricity, you have cold water, which is the end product that you actually need. So that's like a battery, but it costs 1/10 the amount of a battery. But ice storage is very common too. It's used in many stadiums, hospitals, and it can be used on a large scale as well in a 100% clean renewable energy future. What can we do in individual buildings and homes? So I actually want to talk about my own home, which I built. This is one I built in 2017. And there's no gas on the property. It's all electric. And so it has heat pumps, has solar on the roof, has batteries in the garage. And in the house, there are heat pumps. So on the left is an air source heat pump. Well, this is called a ductless mini-split heat pump water heater air conditioner. So it's a very complicated name, but it's kind of very simple idea. Heat pumps do not create heat or cold, they just move it around. They move heat, in this case, from the outside to the inside. So on the right is the outside unit, which draws the heat in. Even if the air is cold, there's still heat in the air, and you can squeeze heat out of the air. And so that's what this does, is it moves heat from outside to inside. And conversely, when it's very hot inside, it moves cold from the air outside to inside. Now, this is very good for mild climates. If you're in an extreme climate where it gets very cold or very hot, you'd want to use a ground source heat pump, where instead of taking the heat out of the air, you'd take it out of the ground, because the ground is a very stable temperature even when there's snow on the ground. And there are now ways to do that by drilling very narrow hole, just a few inches deep, And it used to be that for a ground source heat pump, you'd have to excavate your entire backyard, and it would be very expensive excavation. Now, a company called Dandelion developed a technique to just drill vertically and extract heat deeply. And they now have heat pumps that are ground source heat pumps that are about the same cost as air source heat pumps. And this is very useful for any place that it gets extremely cold or extremely hot. But this, this stays on 24 hours a day, but it only runs when the temperature goes out of the range you want it, that you like it in. It's amazing. It hardly uses any energy. It uses 1/4 the energy as a gas heater or an electric resistance heater. And it keeps the temperature perfect indoors all year. It doesn't matter what the temperature outdoor is like, the temperature indoors stays at a constant, in a constant range. And you can use a heat pump in a water heater too. So this is the water heater heat pump. It looks like any old water heater. But in this case, it takes the heat out of the room that it sits in. So that's what the vents are for. And that heat is exchanged and moved into the water. And as a result, the room is slightly cooler than it was before, but not very much. And in the summer, that's fine because you could just open the door, and then that's another source of air cooling for the house. But again, this works perfectly fine. It uses 1/4 the energy as a gas heater. So water heating and gas heating and air conditioning are the major sources of energy use in your home. Cooking is a very small amount. And by replacing your gas heater, your wood or oil heater with a heat pump, you save a huge amount of money. The cost of installation is about the same as with your traditional appliance. Speaking of cooking, on the right is the induction cooktop stove that I use. It looks very nice, but the key thing is it cooks very evenly. You can control the temperature very well, so even professional chefs like this. You can boil water in half the time as gas, and it doesn't hurt when you touch the top of the stove because it's not actually generating heat on the stove. You need a special pot, which is not expensive. It just has to have an iron or stainless steel base, and it works by exciting molecules in the base of the pot, and the resistance in the base creates heat in the pot itself. So the pot becomes hot, and that's what cooks, but the stove itself is not hot. It becomes a little warm just because heat from the pot conducts down to the stove. But many restaurants are starting to use this, but again, this is a way to eliminate burning of gas, natural gas in your home for cooking. And gas not only creates pollution outside, but creates pollution inside your home as well. So just to give you an idea of how cost-effective all this, okay, and I should mention I also have electric cars. My family has electric cars. And so I've had this 2 years now, and this shows for the first year, but the second year was the same. There's no gas bill, no natural gas bill, no electric bill, no gasoline bill for vehicles at all. And instead, because we have utilities now that are called community choice aggregation utilities, these are utilities that will pay you for the excess electricity that you produced from the solar photovoltaics on your rooftop. So I was paid $530 the first year and $590 the second year by the utility. But the other thing is, by not putting gas in the property, I did not have to pay a hookup fee to the utility for gas, which would have been for me about $6,000, but ranges from $3,000 to $8,000. And just to convert, it's about $1.25 per euro. Gas pipes, I didn't need any of those, so that saved another $6,000 for me, but for typical home would be a $1,000 to $7,000. Electric bill, the typical is $1,000 to $3,000 a year. Gas bill is typically $1,000 to $3,000 per year. Vehicle fuel bill is $1,000 to $4,000. So I eliminated all those bills. So I eliminated $4,000 to $15,000 up front and $3,000 to $10,000 per year forever. So this whole system pays for itself in 5 to 6 years. Well, I should say there are tax credits too. And with the tax credits, it pays itself with 5 to 6 years. Without, it's about 10 years. But these are warranted for 25 years. So after 10 years, everything is free. So I recommend everybody, if you're ever, any new construction, home or commercial building, no gas, just go pure electric. It's cheaper. Why have two sources of energy when you can have one that's more efficient? Even if you have an existing home, it's also cheaper to retrofit. It's fairly straightforward to move, to get rid of a gas heater and get an air source heat pump heater instead. You can have ducted or ductless heating. All these things are possible today. Okay, so let's move on to talk about, well, can we then transition every country of the world to 100% clean renewable energy? Well, we analyzed 143 countries that we had data available for, and these represent 99.7% of all the emissions worldwide. And let's just start with the end-use power demand summed over all these countries. So this is the demand that people actually use for all energy purposes. So that's, again, electricity, transportation, heating, cooling, industry, agriculture, forestry, fishing, military. Summed over all these countries in 2016, it was 12.6 trillion watts, or terawatts of annual average power. If we go to 2050 without changing anything, under a business as usual case, we would go up to 20.3 trillion watts. So that's a huge growth in power demand. But it turns out that if you electrify everything and provide that electricity with clean renewable energy, we reduce power demand without changing our habits by 57%. And that breaks down as follows. Averaged over all sectors, going to battery electric and hydrogen fuel cell vehicles instead of internal combustion engine vehicles, we reduced power demand worldwide 21.7%. Due to transitioning industry, 3.4% reduction. Going to heat pumps for all building heating and cooling, 13.2%. By eliminating the mining, transporting, and refining of fossil fuels and uranium, we go down 12%, because you might not know that 12% of all energy worldwide is just to dig up fuels and process them. And then, compared with the business as usual scenario, we think we can squeeze out about at least 6.6% end-use energy efficiency improvements, which the business as usual scenario has some energy improvements in it. So this kind of this diagram illustrates this transition in a timeline. So we want to transition 80% by 2030 and 100% by 2050. So the top line is going from basically 2018 to 2050 under the business as usual case. If we transition 80% by 2030, well, we're going to go in 100% by 2050. We'd go down those 5 shades of color down to the 100% line in the middle. And each of those lines represents each of the factors that I just discussed. So in the end, we would need to generate 57% less energy, or 8.7 terawatts. And we would do it with combination of onshore wind, 30.5% onshore wind, 14.5% offshore wind, 23% utility scale photovoltaics plus concentrated solar, and then most of the rest is rooftop photovoltaics, and then some geothermal, and some hydroelectric, and tiny amounts of tidal and wave power. So this kind of shows those percentages, and this is summed over all, or averaged over all countries worldwide, and on the right I show our projected mix for Italy, or one. Keep in mind, this is one projected mix. So as I said, worldwide, 30.5% onshore wind, 14.5% offshore wind worldwide, 11% residential rooftop photovoltaics, 14% commercial government rooftop photovoltaics, 19% solar photovoltaic power plants, about 4% concentrated solar, less than 1% geothermal, and about 6% hydro and small amounts of tidal and wave. Actually, in Italy, it's not too far from the world average, a little more onshore, and about the same offshore wind, and lots of solar. So it's a combination, mostly solar and wind. And of course, this is one mix. There are actually many possible mixes, so it's not the only one. But this is based on a resource analysis, what's actually available in Italy. And so this is the land areas required. So worldwide, for these 143 countries, so on the left is a map that shows, okay, well, a lot of the land a lot of the energy will not need land. For example, offshore wind needs no land, tidal wave need no land. Then hydro, we're not increasing the hydro anymore. So there's no new land for hydro. The geothermal is small, so not much there. Rooftop solar does not go on new land. So the only thing that takes up new land is the onshore wind and utility-scale solar and concentrated solar power. So worldwide, we would need about 0.48%, or less than 0.5% of the land for onshore wind. But keep in mind, that land can be used for most anything else. Well, not most anything, but a lot of things like agriculture. It can be used for farmland, grazing land, rangeland, or open space. Or you can put solar on it too. You can put solar on the same wind land. And then 0.17% for utility scale photovoltaics and concentrated solar. So a total of 0.65%. Just to put that in perspective, 1.3% of the entire United States land area is used for the fossil fuel industry. And so that includes the 1.7 million active oil and gas wells, 2.3 million inactive wells, 50,000 new oil and gas wells drilled every year. Keep in mind, we would have to drill, at least in the US alone, 50,000 new wells every year forever. These are new ones every year to keep sustaining this oil and gas industry. But it's also pipelines, gas stations, refineries, storage facilities, you name it. The fossil fuel industry takes up more land than we would need in the US, for example, to transition everything to wind, water, and solar. In Italy, well, with this one scenario, it's only about 2.2% of the land. Another comparison of the land area is about 40% of all land worldwide is used for agriculture, and a few percent is urban areas already. So we would be able to get rid of the entire fossil fuel industry and all the infrastructure associated with it by doing this transition. And so the land area is, as I said, it's multi-purpose land. The next question is, can we keep the grid stable by going to just clean renewable energy? So we broke up these 143 countries. We divided them into 24 world regions. And Europe was one region, for example. And even though we developed plans that would allow each country to power itself with just renewable energy, we envision that it's more efficient actually to trade energy among countries that are nearby. And so we broke up these 143 countries into 24 regions and did studies over 3 years, looking every 30 seconds, over 3 years, can we keep the grid stable in each of these regions? And we found, yes, we can, with no loss of electricity due to the lack of sun or the lack of wind. And as you keep in mind, these scenarios, first of all, they transition everything, all energy, to just electricity powered by wind, water, and solar. And we also had heat, well, electricity plus heat, and we created cold and hydrogen as well. And we included the storage that I talked about, the electricity storage, the heat storage, the cold storage, and the hydrogen storage. And this just shows one example of how, and this is in the United States, the top is all 3 years. It shows on the hourly basis, every hour for 3 years, both the supply and the demand matched each other exactly. On the bottom, this is a 100-day period every hour, it shows the supply and demand matching exactly. So we were able to match supply and demand exactly in every grid everywhere in the world. And then we looked at what's the cost of the resulting energy. Well, here it is. The worldwide cost was 9 cents per kilowatt hour for all energy. And I will compare that to what the business as usual cost is in a minute. But the capital cost of this, so this is a worldwide Green New Deal. This is what it is. This is how much it costs to transition the entire world to clean renewable energy. The capital cost, the present value of the capital cost, it's about 73 trillion, or at least one estimate is. In Europe, it's about 6.2 trillion, and it'd be about 8.2 cents a kilowatt hour. These are US cents. The US is about 9.3 cents, about 7.8 trillion. That's the US Green New Deal, 7.8 trillion. You know, when the Green New Deal was first proposed, people who opposed it said it would cost $100 trillion. But this is based on the actual calculations, what it would cost. And in China, it's about 8.3 cents a kilowatt hour. Sorry, I can't see the bottom of that. But let's just look at the cost compared to business as usual and what we eliminate. Well, in terms of, and this, we're looking here at the yearly cost. So if we actually amortize that upfront cost over time, if we look at that cost over time, how much would we have to pay every year? Because you don't have to pay $78 trillion up front. It's actually spread over from now till 2050. Well, the business as usual energy cost per year is $17.7 trillion per year. That's what energy costs right now. Well, I should say these are 2050 numbers, so that's the 2050 business as usual energy cost, which is a little bit higher than today's energy cost per year. But there's also the health cost, the 7 million people who die every year from air pollution. That's $30 trillion per year. The climate cost is almost $30 trillion per year as well in 2050. Total, what we call social cost of energy for the fossil fuel business as usual case is $76 trillion per year. This is what that cost is. But if we go to the wind, water, solar, remember we reduce our energy use 57%, and the cost of wind energy and solar energy are cheaper than fossil fuels slightly. But it's mostly that 57% reduction in energy use gets us down to $6.8 trillion per year. So instead of $76 trillion per year due to fossil fuels, including the health and climate costs, we're down to $7 trillion almost. So we reduce our energy costs 61% and the total social cost 91%. I mean, that's amazing reduction due to the efficiency of electricity and the cheapness of clean renewable energy. So here's another way to look at it, the costs, averaged over all 24 world regions. In terms of cost per unit energy, it's about 10 cents a kilowatt hour in terms of the energy cost in business as usual. The health cost is another 17 cents a kilowatt hour. The climate cost is another 16 cents a kilowatt hour. So 43 cents a kilowatt hour for business as usual. For wind, water, solar, it's close to 9 cents a kilowatt hour. So it's not a whole lot cheaper per kilowatt hour than the business as usual, 10 cents versus 9 cents. It's a little bit, it's like 10% cheaper. But the real reduction is you have 57% fewer kilowatt hours. This is the key takeaway. You're using much less energy. So even though the cost per unit energy is similar, or even if we're higher, you're just using so much less energy that the whole system is cheaper with wind, water, solar. So there's some ratios near the bottom here. The ratio of the energy cost of wind, water, solar versus business as usual is about 90%. So we're using 10% less energy. Sorry, we have 10% less energy cost. But the social cost, total social cost per kilowatt hour is 23%. In the wind, water, solar case, it's 23% of that in the business as usual case. But we're using 57% less energy. So again, the bottom line is the absolute social cost of wind, water, solar is only about 9% that of business as usual. and the energy cost is about 40%. So we're reducing the cost substantially by going to clean renewable energy. So let me just turn briefly to the policies and what has been done and what is being what is being done and what is happening now. Well, in the United States, surprisingly, there actually have been several laws proposed for the whole country to go to 100% clean renewable energy. In fact, there have been 8 laws since 2015 proposed. There was a House resolution in 2016 going for the U.S. to support a transition to 100% clean renewable energy. There were Senate bills and House bills in 2017, 18, and even in this year there was a bill to go to 100%. In addition to that, the Green New Deal was proposed this year, and that's for the whole United States to go to 100% clean renewable energy. And the Green New Deal, the energy component of the Green New Deal, is based on our plans, starting from the 2009 plan to power the entire world with 100% clean renewable energy by 2030. So this was what I'm showing you here is the scientific basis for the U.S. Green New Deal. But not only that, there actually have been laws. So all those laws that were proposed, none of them have been even voted on. But there have been, since then, 11 laws passed in individual states and territories in the United States. So Washington, D.C. has the most aggressive law, it's a district, of 100% renewable electricity by 2032. So this is actually a law that it's required that the entire district for all people has to go to 100% clean renewable energy. This is just for electricity, not for transportation, heating, cooling, or industry. Hawaii, California, New Mexico, Washington State, and New York have laws to go to 100% renewables by 2045. And Puerto Rico, Nevada, Maine, Wisconsin, and Wyoming have laws to go to 100% renewables by 2050. So these are actual legal, enforceable requirements for these states and territories and districts to go to 100% in the electric power. So they will have to eliminate all gas for electricity, all coal for electricity. This is a requirement under the law. And these also were spurred following the development of individual state 100% maps that we developed for all 50 states, and starting in 2011, that were first published in 2013. But then we also have 134 cities that have committed to 100% clean renewable energy in the US, and 230 cities internationally have committed. And these include many big cities, including Los Angeles and Madison, Wisconsin, Portland, Oregon, San Francisco, San Jose. This week, Philadelphia, Pennsylvania voted unanimously to go to 100% clean renewable energy. For all purposes, by the way, not only electricity. But you can see St. Louis, Missouri, Sarasota, Florida, and Georgetown, Texas. Not only, but also some small towns like in Utah, there's Park City, Utah, Moab, Utah, and little towns in North Carolina. There are actually, I think, 14 towns in North Carolina alone that have committed to 100% clean renewable energy. This is partly due to the combination of science, business, culture, and community. It's because first we developed the plans, and then we engaged in nonprofits, we engaged people who are community leaders, we engaged business leaders and activists, and by combining the science, the business, the culture, and the community, and then the activists have now gone out and gone to these cities and communities and have really helped in this transition. And especially the nonprofits, they really go city by city and try to help each community, give them the information they need to transition. So it's really a grassroots effort in combination with science that has led to all these laws. And it's not only these laws, but also They're companies. There are now 204 international companies that have committed to 100% clean renewable energy, including 8 out of the top 10 companies in the world, which are Google, Microsoft, Apple, JP Morgan Chase, Facebook, Amazon, Johnson & Johnson, and Bank of America. And the only 2 that haven't are, you guessed it, ExxonMobil and Berkshire Hathaway. So, but that is really important because a lot of these companies are, first of all, they're growing in their energy use, and a lot of them have data centers that suck up a lot of energy, so they're committing to provide that energy with wind and solar and geothermal and some hydro and storage, and so this is really beneficial. And as I mentioned, there are a lot of nonprofits there are over 100 nonprofits that have been taken this 100% movement, because it basically is a movement to go to just clean renewable energy. And here are some of the nonprofits. And one of them, well, the Solutions Project is one I helped co-found with Mark Ruffalo and Josh Fox and Marco Krapels. And they, together we started this, but it really expanded. We can't just do this alone. We expanded by engaging lots of people and bringing the science to these nonprofits and to the communities and to business leaders, as I mentioned. And just one more thing, people really want to change. This is a public opinion survey that was done in 2017 of 26,000 people in 13 countries. And the interesting thing is that 82% of the people polled wanted a 100% clean renewable energy world. However, only 66% of these same people believe climate change was a global challenge. So why do people believe in renewable energy even if they don't believe in climate change, if some of them don't believe in climate change? Well, it's because you can believe in renewable energy without having to believe in climate change, because it makes countries energy independent, it reduces costs, it creates jobs, and it makes people proud. It says that 73% of the people says renewables will boost economic growth. So there are that's a good lesson, that we don't have to convince people who don't want to be convinced that climate change is a real problem. If they're satisfied with the solution, going to renewable energy, who cares if they believe in the problem? So let me just summarize what I've talked about. And so in terms of jobs, well, we found from this study that we would create 28 million new excess jobs over loss. So that's 28 million more jobs than lost by doing this transition. We would require about 0.65% of the world's land for for spacing, for wind and solar. We would avoid 7 million air pollution deaths. We would slow, then reverse global warming. We can keep the grid stable throughout the world with 100% renewables. We find that the energy cost per kilowatt hour with wind, water, solar is slightly less than of fossils, but the energy plus health plus climate costs are 1/5 those of fossil fuels per kilowatt hour. And the absolute energy and health and climate costs, when you multiply it by the fact that we are using 57% fewer kilowatt hours, it's 1/11. So if you're interested in more information, all the actual studies are located in the top 2 websites. There are maps for every country that we've studied, well, in this case, it shows 139 countries and 50 states. There are maps at the solutionsproject.org under clean energy. And at the bottom I just mentioned, I just finished a textbook educational textbook that'll be available starting early next year on 100% renewable energy systems for everything. So thank you very much.
Thank you.
Thanks.
Thank you very much. Dunque, come avete visto,
So, as you could see, he was up to our expectations. I think it was really interesting and it was really important because you've seen how we talked about the future. Mark not only told us about the possibility of avoiding the use of fossil fuels, but also about the fact that it is possible to do this in the next third decades, which could seem so difficult since fossil fuels have been used for so long. He showed us how convenient it is because the energy system would still invest trillions of dollars. So I'm not going to reiterate what he has said, but we should hear more about this information in our TV shows and newspapers, because that's what the politics needs to react. So I'll ask the first question. You told us where the world and where innovation can go, how much we can still do with existing technologies, and you've been saying this for years. So my question is, what can we do more? What more can we do? If we look at the last technological revolution we've seen, and if we look 30 years ago, for example, to the phones we had, they were very different. So if 30 years ago we were thinking about the phone industry revolution, well, many things which actually happened, we didn't foresee them. So my question is, what do you expect? What further positive news do you expect? Where do you think there could be some interesting surprise? What could come up from creativity labs what could man come up with their creativity? What do you expect as far as new solutions are concerned, which could make it easy?
So, well, right now I think we have about 95% of the technologies in terms of, like, we have solar panels, we have wind turbines, we have batteries, but even though we have 95%, well, first we do need the remaining 5%. And those remaining 5% are, for example, long-distance jet aircraft, 747s, long-distance ships, long-distance trains, and other types of transport. So that's one area. Then we still want the cost of, for example, offshore wind to come down more. So innovation, and part of that is deployment. When you deploy technologies, the more you deploy them, generally that results in more research and more innovation and competition, and that drives the cost down. I do not think we need any miracles technologies. So sure, we can have new technologies, we can have technologies that reduce the cost more, we can improve the existing technologies, but it's really focusing on the things that are maybe more expensive now, like tidal power, wave power, offshore wind, concentrated solar, batteries, even electric cars, and trying to drive those costs down, partly through deployment and partly through more research and development.
Okay, thank you. Grazie mille. Ora direi possiamo...
Thank you very much. I think that we can open our debate. I'd like you to ask short questions because I've already seen a lot of hands raised. So the shorter your question is, the greater chance Mark will have to answer your questions. So, please. Thank you for this wonderful speech. My question is really simple. Which difficulties could be found in the application of these new technologies? For example, not only from an economic standpoint, and not only in the USA, where people are already aware of this issue.
The biggest challenges are social and political, I believe. I don't think there's a technical or economic limitation to transitioning, but there is social and political pushback, partly due to, sure, the fossil fuel industry doesn't want us to change, so they will push back. But even in communities, a lot of times the communities don't want to see a wind turbine nearby or a wind farm, and so there will be pushback there. But we all have to keep in mind that, first of all, we're removing infrastructure at the same time that we're adding infrastructure. And nobody wants to add any technology to the environment, but we have to get our energy from somewhere. So the real question is, would you rather get it from gas or coal or nuclear or oil, or would you rather get it from clean renewable energy? But I think, yeah, the biggest obstacles are social and political, because the fossil fuel industry has been here, well, if you count the coal, it's been here hundreds of years, but they have a lot of money and they donate to a lot of lawmakers, at least in the US they do, and that results in half the politicians being against a rapid transition. But on the other hand, the costs have come down so much that the public in particular, but also policymakers in many states and countries, realize that's the best way forward economically because it's so cheap.
Bene, c'è una seconda domanda qua.
Okay, another question here.
Grazie, buonasera.
Thank you. Good evening. Just a general question. Also, in the previous speech, we've also seen that renewables have been increasing in the last years, but we are lagging behind as far in the last 30 years. What do you think about this? Could we say that it is due to the political class which didn't want to which didn't want to bet on these energies, or do you think that scientific research also stuck to a theory instead of calculating something which should have been calculated from an economic standpoint? For example, the conversion, the transition of old plants. So, was it because the political class couldn't actually propose efficiently good solutions?
Well, I think it differs in every country. I should point out that there are actually 8 countries of the world that are at or right near 100% renewable electricity. And those countries include Iceland, Norway, Costa Rica, Tajikistan, Albania, Paraguay, Kenya, and Scotland. They're all either at or very close to 100% renewables. Most of them have a lot of hydro, like Albania, Paraguay, Tajikistan are all mostly hydro, and in fact most of the others are too, but they also have wind and geothermal in some cases. So it's part of its resources that are obviously there already, and the other is the technology has come down. Only recently has it become really cheap. I mean, this year, last year, maybe the year before, it was inexpensive. But before that, you could argue that it was, without subsidy, it was a little more expensive than conventional fuels. And so people are cautious. They don't want to naturally jump into something they're not familiar with. It sometimes takes examples. You have to see examples to be confident to take the next step. And so in some places, fortunately, like in California, they've been working on, they put wind farms in the 1970s, so they actually had experience in the 1970s, and a lot of solar went up in between, so it wasn't like they just started from nowhere. They actually had a long learning curve, and then all of a sudden it just took off, and they also have the political will as well. So some places have the political will just because they've had the experience. Some places have political will because the costs are very low. So I think it's migrating. Places that have typically been against renewables are now for them. You'd be surprised in the United States, actually, the 9 out of the 10 states that have the highest wind power are all dominated by the Republican Party, because wind is so cheap. It's not because they have policies that have favored it. It's because it's much cheaper than everything else. And so this will happen in other places as these renewable costs come down even more. You'll see places adopting them because it's silly not to. You just waste a lot of money. Just like I showed with the house. I thought it would be expensive, but it's so much cheaper. And I think as more people do that, they will realize that. Same thing with an electric car. If you drive an electric car, you will save, well, in the US, depending on your driving habits, but $20,000 over 15 years by driving an electric car because the cost of the fuel is 1/4 that of gasoline. And in Europe, the fuel costs are even like twice US costs, so you'd probably save even more. But once people realize that, they would never go back. I mean, I think once you go to an electric car, you would never go back to a gasoline car because it's so much better in terms of not only the fuel, but the safety, the acceleration, fewer repairs, the safety in terms of you won't turn over as much, it won't explode if you crash. It just has more crush space in the center. So there's a lot of benefits of these things that people won't realize until they actually try them out.
Grazie. C'era una domanda qua, poi una là in fondo.
Okay, another question here, and then one over there. First of all, thank you for this great conference. But a question comes to mind. The fact that a car and also an airplane have great consumptions. Today, are there any batteries which can actually supply airplanes and cars? And connected to this, we've talked about wind energy and solar energy, but we could also use some other forms. For example, in Iceland, where there is a great volcano activity, well, Iceland could obtain a lot of its energy thanks to underwater heat.
So, Iceland, sure, geothermal is part of our solution. So countries that have a lot of geothermal, Italy has geothermal too. In fact, the very first geothermal electric power plant in the world was in Italy. And that's definitely a source of energy. So it's not just wind and solar for sure, but wind and solar, though, because of the magnitude of the amount you need on a worldwide scale, will be over 90% of the total. Geothermal will probably be geothermal for electricity will be 1%. For heat, geothermal heat will comprise a great amount. So ground source heat pumps, the heat pumps I talked about, when you take the heat out of the ground, that's geothermal heating as well. But there are also places that are near volcanoes where you can get direct heat even easier. In terms of the batteries, yeah, there are already cars that have 500-kilometer range. That's not a problem, and I'm sure they'll go up to 700-800 kilometers. Most people don't need that range. For 95% of commutes, you don't need 500 kilometers, but they're there. Aircraft, it's a different story. We do have aircraft already that are short distance. They go several hundred kilometers, and it's anticipated that by 2022, 23 might have up to 1,500-kilometer electric aircraft. Probably not farther than that. Farther than that will be hydrogen fuel cell, I think.
C'è una domanda là in fondo, la mano, ecco. Poi ne faccio una.
Another question over there, and then a last one. My compliments for your speech. I would like to ask two questions, one of a political nature and one of technical nature. The first one concerns Trump's policy, who has proposed mining techniques through cracking, and he is also supporting coal, the use of coal. So, how can you put together your vision and Trump's policy? The other question, a technical question. A lot of years ago, we talked about the possibility of obtaining energy thanks to nuclear fusion. It was the talk of the town a lot of years ago, and because thanks to nuclear fusion we could obtain such energy that we could actually eliminate oil. So I would like to know if in America research is still being conducted about that.
Yes, there is research being conducted on nuclear fusion. However, we don't support any technology that's not actually available in some form or another, except for these long-distance transport, because we need to solve the problem, 80% of the problem in 10 years. So we can't put all our eggs in a basket with some technology that may or may not exist anytime. And we know we can solve the problem with these renewable energies, so this is what we think we should focus on. So even though there is research being conducted on that, that's not something that we have any expectation that will help solve the problem or that we even support researching, because people have been saying for nuclear fusion, they've been talking about it for decades, and there's been no evidence that it's actually going to come to fruition. With regard to mining, well, when we mine you will have mining with renewables, but it's not for the fuel. Like, we will not have to dig 50,000 oil and gas wells every year in the US like we do right now, and tens of thousands everywhere else every year. There's one-time mining for the materials that you need to build devices for, well, steel and concrete. You'll need some, and there's some rare earths. But it's one-time mining, and then that can be recycled over time. Now, the mining will actually be conducted with clean renewable energy as well. So we will eliminate all the energy, the coal, the gas, and the oil that is used for mining. And so so it will be wind, water, solar as well.
La domanda era anche se Trump sta cercando di fare tornare il carbone, o se comunque il carbone ormai, diciamo, è morto. Che futuro vedi per il carbone negli Stati Uniti, nel senso, dal tuo scenario? Can you hear? No?
I didn't hear that. Okay.
The question also concerned the future you see for coal. Will Trump succeed in reviving coal, or will it be dead?
So, no. So Trump, when he came to office, he promised to revive coal. But since then, coal production has been cut in half. It's actually more coal plants have been closed under Trump than anybody else I know. And in fact, coal is now only about 23% or something of US electricity. It was, when Trump started, it was like 37 to 40% of the electricity. So every year it's gone down, and it's going to go down even more. There's really nothing stopping it from going down.
Adesso faccio io un paio di domande che sono molto pratiche.
I'll ask a couple of questions which are actually concrete for us as individuals and as a city. This big transition, well, you've showed us that this big transition is actually possible, but the time is so little. 30 years is a short time, so it's something we need to support. So what can we do as a single individuals, also keeping into account the fact that not everybody can invest a lot of money in a car, which today still costs 30,000 euros. Okay, you can save money if you look at the long term, for example in 10 years, but at the moment maybe someone doesn't have that kind of money. So could you give us a couple of suggestions about what to do as a single individuals? Well, in my last book, which is entitled "The Climate Has Already Changed," at the end I put 100 actions that we could actually perform to help climate change. And one is the fact is not invest in fossil fuels or in coal mines and so on. So, from a concrete standpoint, what are the main 2-3 things that a common family can do to help this transition?
Yes, so, well, individuals can do a lot in their own home. I mean, light bulbs. Instead of using incandescent light bulbs, use LED light bulbs. So switch those out as soon as you can. They use 1/10 the energy, so your electricity bill will go down. Weatherizing your home, putting a little more insulation under cracks under windows. That's a very inexpensive way to reduce energy loss. And then the next time you do have to change your water heater or air heater, or if you have air conditioning, go to a heat pump. I mean, you may not want to go out right now and buy one, but the next time it breaks down, the next time you buy something, make sure it's not a gasoline or fossil fuel-based appliance. Every appliance you buy from now on, make sure it's electric. And that way, you're not actually spending additional money. You're just you have a choice. You can buy a gas stove or an electric induction cooktop stove. They cost the same. So why buy the gas stove? Because then you'll have to pay for fuel, and you'll pollute, and you'll allow. Because when you buy gas stove, you're not only burning the gas that's coming to your stove, but you're also somebody's drilling for gas somewhere in the world and having it piped to you, and that takes a lot of energy and pollution as well. But so people can do a lot of things individually. You can reduce your commutes, travel less, and and telecommute more, work from home, take public transportation, bicycle more. But you can also support policymakers that support renewable energy, clean renewable energy. That's another thing.
And for policymaker, per le città, siccome qua
About cities, of course, we will have some politicians among the public, among the audience, and maybe there are some young people who are demonstrating and would like the municipality to act. We know that on a municipality level, there is not so much money to invest, but maybe we could do something on a municipality scale as well. So, what can we ask, or what can we demand from our municipalities? Which actions are the least expensive and efficient?
Well, I think the first thing to do is to educate the municipal leaders into what's possible. Now, a municipality can actually pass a resolution that might not be binding to go to 100% renewable energy. And so they can commit to it. So the first thing is to have a commitment to do it, and the next thing is to figure out how to do it. So, if the policymakers don't want to actually pass a law, or if they can't pass a law, they might be able to pass a resolution saying we commit to it, and then they can investigate what are the things we can do. And the community leaders can also can educate the people in the community about what is possible. They can come up with a little booklet saying you can do this, this, and this, or even look at the costs of doing this, this, and this. This is what my Palo Alto, a city that I live near, they did that. They investigated the costs of anybody transitioning their own home to retrofit their own home to renewable energy. What would it cost for each type of appliance? And they passed this out to the public. And I should say, like, another town right near me, 2 weeks ago, they banned, Menlo Park, California, banned natural gas in all new buildings. So they literally passed, there's no new gas in any commercial building or residential building anymore after January 1st, 2020. And this was a surprise. Actually, a few weeks before, Berkeley passed a similar ban. And in a few weeks, San Jose will pass a ban as well. So this is spreading through lots of communities where they're banning new construction with gas pipes or anything to the home, so that you don't have this infrastructure that's supporting this energy source.
Bene, ci sono
Okay,
qualche domanda?
is there any further question? Otherwise, I have another question, and then okay, the last question here.
Ho una domanda un po' tecnica.
I've got a quite technical question. Do you see fossil fuels synthetical fossil fuels playing a role alongside hydrogen?
Well, we're trying to solve the air pollution problem as well as the climate problem. So while synthetic fossil fuels reduce some greenhouse gas emissions, you still burn them and you create air pollution. So we're trying to eliminate that. So no, we don't support that. I realize that some people are developing them, but it's not part of our energy plans for synthetic fuels, just because it's combustion. And plus that also allows the whole infrastructure to stay in place for this fossil fuel infrastructure, and it discourages people from getting electric cars as well. So.
For hydrogen?
Oh.
And hydrogen also?
Oh yeah, so hydrogen, we support the use of hydrogen in fuel cells, not combustion. So hydrogen produced by electricity, so by electrolysis. and where the electricity is from wind and water and solar power. But yeah, hydrogen fuel cell cars, buses, trucks, planes are fine. It'll turn out that it's much less efficient than battery electric for short distance transport. It's really only most efficient for long distance heavy transport.
Molto bene, io direi che davvero oggi abbiamo aperto.
Very good. I'd say that today we've opened a window on the future. Oh, there's the last question. Sorry, I didn't see you. I would like to know if, thanks to this great development of renewable energies, could there be a problem of disposal in the future? I mean, for the infrastructures and the facilities which are used, for example, batteries, solar panels, or collectors, and so on.
Well, there's always a challenge, but I don't think it's not nearly so much of an issue compared to the fossil fuels, because take solar panels, they will last 25 to 30 years. In fact, they're warranted for at least 25 years. And then a lot of the components can be recycled. Whether they are recycled is a different question, but there is an incentive in laws in some places to recycle many of the components. But the thing is, this is one time. Let's say, even in the worst case, let's say you used the solar panel and you threw it out. That is still orders of magnitude less waste than in mining, having to dig up fossil fuels every day, every year, everywhere. I mean, as I mentioned, I'll mention again, 50,000 new oil and gas wells every year in one country alone. And you can't sustain that. It just destroys an entire country when you do that.
Bene, allora io direi che davvero possiamo
Okay, I would like to thank both Mark Jacobson and Bergamo Scienza because they gave us the chance to open this window on the future. I am always telling my students that climate change is not a scientific question any longer, because it's clear that man is changing the planet's climate, and it's clear what is going to happen in the future. But Mark today has told us that it's not a technological matter and it's not an economic matter, because from a technical and economic standpoint it is feasible. It is also a social and political question, a political issue. So it's important to talk about this during this occasion. So thanks Bergamo Scienza, thanks Mark Jacobson. One last communication. There's an online survey which you can find online, but also at the exit, at the help desk, and you can fill in the survey to indicate your satisfaction with Bergamo Scienza initiatives. Thank you.